There is a game you can only win by falling asleep. 100 levels. Level 1 is a pebble on the ground, doing nothing at all. Level 100 is the shape of time, bending around a star. Wherever you drift off tonight, that is your score. So settle into the position you sleep in. Let your shoulders drop. Let the day close behind you, quietly like a door. We begin, as all of physics begins, with something almost embarrassingly simple. A small gray pebble sitting on the ground, perfectly still. It looks like nothing. It is the first rung of a ladder that reaches all the way up to the deepest structure of reality. Level 1. Begin with a pebble resting on a windowsill. It does nothing, and that is already interesting. When we say the pebble is at rest, we are quietly comparing it to the sill, the wall, the room. Rest is not a private property of the stone. It is a claim about its surroundings, a relationship, like being beside something or beneath something. Hold that thought gently. It will matter more than almost anything else. Level 2. Now let the pebble roll off the sill or a cat cross the floor. Motion is simply a change of place over time, and noticing it is the oldest observation there is. Long before anyone could write, people watched the sun slide across the sky and the river slide past the bank. All of physics grows from this one quiet habit, watching where things are and watching where they go. Level 3. If motion is a change of place, we should ask what a place is. Picture describing where your keys are. You never say it in absolute terms. You say on the table, by the door, 2 steps from the bed. Position only ever means position relative to something else. There is no address written on empty space itself. Every location is measured from a chosen landmark, and the choice is ours. Level 4. Once position can change, we can ask how quickly it changes, and that is all speed is. A person out walking covers perhaps 5 kilometers in an hour. A train passing the same path covers 100 or more. Same road, same direction, very different pace. Speed is just distance traded for time, a simple ratio, and yet it is the first true measurement in our story. Numbers have now entered the picture, softly. Level 5. Speed alone, though, leaves something out. Imagine 2 cars on a quiet highway at night, each moving at exactly 60 kilometers per hour, but heading in opposite directions. Their speeds are identical. Their situations could not be more different. So physicists pair speed with a heading and call the pair velocity. Direction matters as much as pace. A thing is not just moving fast or slow. It is moving fast or slow towards somewhere. Level 6. Now that we can describe motion, notice one motion that never asks permission. Let go of a spoon, a sock, a drop of water, and each one falls. Not sideways, not upward, but down, always down, toward the same floor. Whatever you release, the world seems to pull it the same way. That sameness is strange when you sit with it. Heavy things and light things share one downward invitation. Why they do is a long story, and we will walk it slowly. Level 7. And yet some things politely refuse. A cork pushed under the bathwater slips back up to the surface. A balloon filled with helium drifts toward the ceiling instead of the floor. Falling, it turns out, is not a rule without exceptions. It is a competition, and sometimes the surroundings win. What exactly the water and the air are doing is a lovely piece of reasoning. and it is waiting for us at level 18, level 8. There is also a kind of motion that goes nowhere at all. Think of a slow ceiling fan or a record turning on a player. The fan blade ends the hour exactly where it began, yet it never stopped moving. Spinning is motion of a curious sort. The position barely changes, but the direction of travel changes constantly, moment by moment, around and around. Rotation will return many times in our climb, wearing different costumes. Level 9. Motion can also be handed from one thing to another. Drop a rubber ball, and it bounces back up, though never quite as high as it started. Roll one marble into another, and the first slows while the second sets off. Collisions pass motion along, the way a whispered message passes down a row of children. Some is always kept, some is always shared, and the bookkeeping of that sharing has a name waiting a few levels up. Level 10, which brings us to the gentlest puzzle of all. Everything we set moving seems, if left alone, to slow down and stop. The marble stills, the ball settles, the sled glides to rest in the snow. For nearly 2,000 years, wise people concluded that rest is simply what motion wants. It seems obvious. It is also, quietly, wrong, and seeing why is the first great turning point of physics. The truth is waiting at level 15. For now, just drift with the sled. You have climbed 10 levels now, and so far you have mostly watched the world move. From here on, we stop simply watching and begin, very gently, to measure. 11. Watching taught us that things move. Measuring lets us say exactly how. A meter is not found anywhere in nature. It is an agreement, a quiet promise between strangers about what one length will mean. The meter was once the length of a metal bar kept carefully in Paris. Today, it is defined by how far light travels in a tiny sliver of a second, and the second itself is counted by a cesium atom, vibrating just over 9 billion times as each one passes. Units are handshakes across centuries. Once we shake hands, we can begin level 12. With units agreed, the first thing worth measuring is motion itself. Speed is simple enough, a distance covered in a time, like 60 kilometers in 1 hour. Velocity is speed with a direction attached, and the direction matters more than it seems. Picture two trains leaving the same station at the same speed, one heading north, one heading south. Their speeds are identical. Their velocities are opposites. To predict where something will be, you must know not only how fast it moves, but which way. And turning, it turns out, changes velocity too. That thought is waiting at the next level, level 13. If velocity is speed with a direction, then acceleration is any change in that velocity. Speeding up is acceleration. Slowing down is acceleration. Even turning at a perfectly steady speed is acceleration, because the direction is changing. You already know what this feels like. An elevator starts to rise, and for a moment your stomach presses downward, heavier than usual. When the elevator slows near the top, you feel briefly pleasantly light. Your body is a quiet instrument that measures acceleration all day long. Hold on to that feeling. Much later, it will help us understand gravity itself. Level 14. To change how something moves, you must push it. So now we ask what resists the push. Mass is, roughly speaking, the amount of matter in a thing, and it shows itself as reluctance. An empty shopping cart leaps forward at the lightest touch. The same cart, fully loaded, answers the same push with a slow, dignified drift. Nothing about the wheels has changed. What changed is how much matter must be persuaded to move. Mass is that stubbornness, and we measure it in kilograms. It has a second face, a familiar one, waiting at level 20, level 15. Several levels ago, we noticed that everything in motion seems, sooner or later, to stop, and we let that mystery rest. Galileo picked it up with two polished ramps. A ball rolled down one ramp and up the other, rising to nearly the height where it started. When he made the second ramp shallower, the ball rolled farther to reach that same height. And if the second ramp were perfectly flat and perfectly smooth, the ball would roll on forever, never needing to stop at all. Motion does not die on its own. Something has been stopping it, and that something is next. Level 16. The culprit Galileo suspected has a name, and the name is friction. Slide a book across a table and it whispers to a halt, not because motion naturally fades, but because two surfaces are quietly gripping each other. Up close, even polished surfaces are tiny mountain ranges, catching and dragging as they pass. Friction is the hidden hand that made the whole world seem to prefer rest, yet it is also a friend. Without friction, your feet could not grip the floor, and you could never walk across a room. The same gentle hand that stops things also holds things. Level 17. Air is a kind of surface too, in its own thin way, and it drags on everything that moves through it. Drop a hammer and a feather together, and the feather drifts down lazily, held back by the air its broad shape must push aside. For centuries, this made it seem that heavy things simply fall faster. Then an astronaut on the moon, during the Apollo 15 mission, dropped a hammer and a falcon feather side by side. With no air at all, they fell together and landed together. Why everything falls alike is a deep question, waiting far up this mountain. Level 18. Near the bottom of this climb, we watched things float and wondered how the water chooses. Density is the answer taking shape. It is how much mass is packed into a given amount of space. Steel is denser than water, so a solid steel bar sinks without hesitation. But a steel ship is mostly hollow, steel wrapped around great rooms of air. Averaged over its whole shape, the ship is less dense than the sea, and so the sea holds it up. It is not the material alone that decides. It is the material and the emptiness. Taken together, level 19, the sea holds a ship up by pressing on its hull, and that pressing brings us to pressure. Pressure is not simply how hard you push, but how hard you push on each small patch of surface. Snowshoes spread a person's weight across a wide frame, so every patch of snow carries only a little, and the snow holds firm. A needle gathers a gentle push onto a point so fine that cloth gives way at once. The same force, spread thin or concentrated, does very different things. The atmosphere is pressing on you this way right now, softly, from every side. Level 20. We promised that mass has a second face, and here it is, called weight. Mass is how much matter you are. Weight is how hard gravity pulls on that matter, and the pull depends on where you stand. On the moon, gravity pulls about 1/6 as strongly as it does here, so a traveler there weighs about 1/6 of what the scale said at home. Yet nothing of them is missing. Shake a bowling ball from side to side there, and it fights your hands just as it does here. You can weigh less without being less. Gravity itself is waiting a few levels up. All the careful measuring is finished now. Falling bodies timed, planets tracked, motion written down in patient notebooks. What happens next is that one quiet man, Isaac Newton, gathers every one of those threads and ties them into a single machine. Level 21. Galileo suspected that motion, left alone, simply continues, and Newton made that suspicion into the first law of his new system. A body at rest stays at rest, and a body in motion keeps moving in a straight line at a steady speed unless something pushes or pulls on it. The universe's default setting, in other words, is to keep doing whatever it is already doing. Think of a hockey puck gliding across smooth ice, needing nothing at all to continue. Rest is not the natural state of things. Coasting is. Every force we meet from here on is not what keeps motion alive, but what changes it. That change is waiting one level up, level 22. If the first law says motion continues on its own, the second law says what a push actually does. Force equals mass times acceleration. Spoken slowly, it means this. When you push on something, you change its velocity, and how quickly that velocity changes depends on how much stuff you are pushing. You know this from the grocery store. An empty shopping cart glides forward at the lightest touch, while a full one answers the same push with a slow, reluctant drift. Same force, more mass, less acceleration. This one small sentence lets you predict the motion of carts, carriages, cannonballs, and, as we will soon see, the moon itself, level 23. The second law told us what a force does. The third tells us that forces never come alone. For every action, there is an equal and opposite reaction. Whenever one thing pushes on another, the other pushes back just as hard in the opposite direction. When you walk, your foot presses the earth backward, and the earth presses you forward, which is the only reason you go anywhere at all. The planet recoils beneath every step by an amount far too small to notice, but not zero. A rowboat drifts backward as you step onto the dock. Nothing in this universe pushes without being pushed. Even gravity, as we are about to see, is mutual, level 24. And now the famous apple, which really did set Newton wondering, though it likely never struck his head. He asked whether the pull that drops an apple might be the very same pull that holds the moon, stretching unbroken from the orchard to the sky. His law of universal gravitation says yes. Every mass in the universe attracts every other, and the attraction weakens with the square of the distance. Move twice as far away and the pull drops to a quarter. 3 times as far, a ninth. One rule, written once, governing apples, moons, planets, and the slow tides of the sea. The heavens and the earth turned out to share a single law, level 25. To show what his law could do, Newton imagined a cannon on a very tall mountain, firing gently far above the air. Fired softly, the ball arcs down and lands nearby like any thrown stone. Fired a little harder, it lands farther away, the curve of its fall stretching out. Now fire it hard enough, he said, and something lovely happens. The ball falls, but the Earth's surface curves away beneath it at exactly the same rate. The ball keeps falling, and keeps missing the ground all the way around the world. A thrown ball and an orbiting body are the same motion, differing only in speed. Hold that image while you drift toward the next level, level 26. That endless falling is exactly what the moon is doing right now, high above your roof. The moon is not resting on anything, and no wire holds it up. It is falling toward the earth at every moment, pulled by the same gravity that pulls a dropped key. But the moon also moves sideways, fast enough that as it falls, the earth keeps curving away beneath it. So it circles, month after month, falling forever without ever arriving. Every satellite, every planet around the sun is doing the same patient thing. An orbit is not the absence of gravity. It is gravity, perfectly balanced against sideways motion, and it can go on for billions of years. Level 27. The same moon that falls around us also reaches down and gently moves our oceans. Because gravity weakens with distance, the moon pulls the ocean on the near side of the earth a little harder than it pulls the earth itself. The ocean on the far side is pulled a little less and gets left slightly behind. The result is two soft bulges of water, one facing the moon and one facing away, and as the earth turns beneath them, most shores meet two high tides each day. If you have ever sat on a beach and watched the water slowly climb the sand, you are watching the moon's uneven pull written in salt water. The sun adds its own smaller voice, level 28. Forces, then, are everywhere, but physics gives a special name to a force that actually moves something. Work, in this precise sense, is force applied through a distance. Lift a heavy suitcase from the floor to a shelf, and you have done work on it. The force of your arms acted along the path it traveled, yet stand still holding that same suitcase, and in the physicist's ledger you have done no work at all, however tired your arms become. The suitcase went nowhere, so nothing was transferred to it. That feels unfair, and yet the strictness is the point. Work measures something being handed from you to the suitcase, and that something has a name, waiting at the next level, level 29. The thing that work hands over is called energy, and it is the quiet currency behind everything in this story. When you lifted the suitcase, the work you did was stored in it as potential energy, energy of position, patiently held by gravity. If the suitcase slips off the shelf, that stored amount turns into kinetic energy, the energy of motion, growing as it falls. A child on a swing trades the two back and forth, height becoming speed, becoming height again over and over. Energy changes costume constantly, but the total, carefully counted, never changes. Nothing in physics moves without it, and nothing spends it without a record. That bookkeeping will follow us all the way to level 100, level 30. With work and energy in hand, we can finally understand the oldest tools in the world. A lever, a pulley, a ramp. Each one lets a small force do a big job, and for thousands of years that looked like a kind of magic. It is not magic, it is a trade. Press the long end of a lever gently through a wide arc, and the short end lifts a heavy load through a small one. Less force, more distance, and the work comes out exactly the same. No machine ever built creates energy. It only rearranges the terms of the bargain. Nothing in this universe is free, and a few levels up, that rule will earn a grander name. Newton gave us the machinery of the world, forces and masses, and the clean mathematics of motion. Underneath that machinery, physics was about to discover its bookkeeping, a small set of hidden currencies that the universe counts perfectly and never loses. Level 31. Beneath all of Newton's pushes and pulls, there is a ledger, and the ledger always balances. Physicists call the quantity in that ledger energy, and its single strange rule is that it can never be created and never destroyed. It only changes costume. Lift a book onto a shelf, and you have paid energy from your muscles into the book's height. Let it fall, and the height turns back into motion. When it lands, the motion becomes a soft thump of sound and a whisper of warmth in the floor. Nothing is ever lost along the way. Roughly speaking, every event in the universe is energy changing from one costume to another, while the total, counted honestly, stays exactly the same. In all of history, that total has never once been caught changing. Level 32. Energy is not the only quantity the universe refuses to misplace. There is a second currency called momentum, which is, roughly speaking, the sheer quantity of motion a thing carries, its mass multiplied by its velocity. A heavy barge drifting slowly can carry as much momentum as a light runner sprinting, weight and speed traded against each other. The rule is simple and absolute. When objects push on one another, momentum only passes between them, and the total never changes. Step off a small rowboat onto a dock, and the boat glides backward beneath your feet, carrying away exactly the momentum you carried forward. In every collision ever observed, from billiard balls to colliding galaxies, this account has balanced perfectly. Collisions, in fact, are where momentum shows itself most clearly, and they are next. Level 33. Watch two billiard balls meet, and you are watching momentum change hands. In some collisions, called elastic, the energy of motion is preserved almost completely. The balls click apart, carrying nearly all the liveliness they arrived with. In others, called inelastic, something stranger happens. Drop a ball of soft clay onto the floor, and it lands with a dull thud and simply stops. Its momentum passes into the whole earth, far too vast to notice, but its energy of motion seems to vanish outright. The ledger from level 31 insists that nothing truly vanishes, so the missing motion must have slipped into some smaller, quieter costume. It has. Where it went is one of the loveliest secrets in this whole story, and it is waiting for you at level 39. Level 34. There is a third currency kept for things that spin. It is called angular momentum, and it depends not only on how fast something turns, but on how far its mass sits from the center. Picture a figure skater spinning slowly with her arms stretched wide. When she pulls her arms in close to her body, she has not pushed against anything, and yet she blurs into a whirl. Her total angular momentum could not change, so when her mass moved inward, her speed had to rise to keep the account balanced. The same bookkeeping shapes far grander things. Collapsing clouds of gas spin themselves into flattened, whirling disks, which is, in essence, why the planets circle the sun in a single plane. The skater and the solar system obey one rule, level 35. With these currencies in hand, Watch what happens when energy is made to sway back and forth. Hang a weight from a spring, pull it down a little, and let go. The spring tugs it back toward home, it overshoots, and the spring tugs again from the other side. Any force that always pulls a thing back toward its resting place is called a restoring force, and restoring forces produce the gentlest motion in physics, a smooth, even swinging that repeats and repeats. A pendulum does the same, trading energy of height for energy of motion at the bottom of every swing, then trading it back. Galileo noticed that a gently swinging pendulum keeps almost perfect time, swing after swing, whether its arc is a little wider or a little narrower, which is why pendulums kept the world's clocks honest for centuries. This calm rhythm is about to become the heartbeat of everything ahead, level 36. Now let that swinging spread from place to place, and you have a wave. Drop a pebble into a still pond, and rings glide outward across the surface. Here is the quiet surprise. The water itself barely travels. A leaf floating on the pond only bobs up and down as each ring passes beneath it, ending up almost exactly where it began. What actually moves outward is the disturbance, the pattern of rising and falling, and with it, the energy of the pebble's splash. A wave is energy on a journey without cargo, delivered without any material making the trip. Each bit of water simply nudges the next, the way a roomer crosses a crowded room while every person stays in their seat. Hold on to that idea. Waves will carry most of the rest of this story. Level 37. One of these traveling disturbances may be passing through the air around you right now, soft and slow. Sound is a wave of pressure. A voice, a bell, a closing door. Each one squeezes the nearby air a little, and that squeeze pushes on the air beside it, ripple after ripple, until the pattern arrives and gently presses on your eardrum. In ordinary air, these ripples travel at roughly 340 meters every second, which is why distant thunder arrives long after the flash. And because sound is only a relay of collisions between molecules, it needs something to travel through. In the near emptiness between the planets, there is almost nothing to pass the squeeze along, and so space is, quite truly, perfectly silent. Level 38, every swinging thing, it turns out, has a rhythm it prefers, and there is a quiet magic in matching it. Think of pushing a child on a playground swing. Push at random moments, and you mostly fight yourself, each shove undoing the last. Push gently at exactly the moment the swing returns to you, again and again, and each small push adds to all the ones before. The swing climbs higher and higher from almost no effort. This is resonance, the growth of large motion from small pushes delivered in perfect time. It is how a singer's steady note can set a wine glass trembling across the room, and why soldiers walk out of step when they cross a footbridge. Matching an object's natural rhythm is the softest way to move it greatly. Level 39, and now the promise from level 33 can be kept. When the clay ball landed and stopped, its motion did not vanish. It scattered. The visible movement of one object broke apart into trillions of invisible movements, each atom in the clay and the floor jiggling a little faster than before. That jiggling has a familiar name. We call it heat. Temperature, in essence, is a measure of how vigorously the atoms of a thing are trembling in place. A warm mug feels warm because its busy atoms drum against the atoms of your palm. Rub your hands together on a cold night, and you are pouring ordered motion into disordered motion and feeling it as warmth. The missing motion was never lost. It only became too small to see. Level 40. If temperature is trembling, then a gas is trembling set loose. In air, the molecules are not held in place at all. They fly freely, collide and scatter, each one darting hundreds of times its own width between one encounter and the next. A ceaseless, invisible weather filling every room. Press your thumb gently against an inflated balloon, and you can feel them. What pushes back is not the rubber alone, but a drum roll of countless molecules striking the inside surface. So many strikes each second that the patter blends into one smooth, steady pressure. Squeeze the balloon smaller and the same molecules strike the walls more often, so the push grows. Warm them, and they strike harder. And hidden inside this restless crowd is the reason time flows in only one direction. That secret is waiting a few levels up. We have spent the last several levels finding out where motion hides, how the energy of a rolling ball slips quietly into the trembling of atoms that we call heat. Now we ask a stranger and softer question, which is why that energy, once it has hidden, never finds its own way back. Level 41. Physicists of the 1800s gathered all of this into a single statement called the first law of thermodynamics. It says that energy is conserved, always, but only if you count heat as one of its forms. James Joule showed this with a paddle wheel turning in a barrel of water, driven by a slowly falling weight. The water grew warmer by exactly the amount of motion the weight gave up. Nothing was lost. Nothing was created. Energy only changed its clothes. This sounds like good news, but it carries a quiet warning. If energy can never be created, then no machine will ever give you more work than you feed into it. Engineers sometimes state the first law as a small joke. You cannot win. You can only trade one form of energy for another, and every trade is recorded down to the last trembling atom. The next law is stricter still, level 42. The first law says energy is conserved, yet it says nothing about which way energy prefers to move. For that, watch a cup of coffee left on a desk. Its warmth drains into the cool air of the room, slowly and steadily, until cup and room agree on one temperature. It never happens the other way around. The room never gathers its scattered warmth and pours it back to make the coffee hot again. Heat, left to itself, flows only downhill, from hot to cold, and it never climbs back up on its own. This one-way habit is among the most dependable facts ever observed. If the first law says you cannot win, this rule whispers that you cannot even break even. A little warmth always leaks away into places you can never collect it from. Why the universe insists on this direction is a lovely question. The answer, waiting at the next level, is counting. Level 43. To see why heat only flows downhill, we must learn to count. Picture a fresh deck of cards arranged neatly by suit and number. There is essentially one way for the deck to be perfectly ordered and an astronomical number of ways for it to be shuffled. So when you shuffle, you always drift toward disorder, not because order is forbidden, but because it is outnumbered beyond imagining. Ludwig Boltzmann realized that atoms play the same game. The energy in a warm room can be shared among trillions of trembling molecules in vastly more ways than it can sit concentrated in one hot cup. Physicists gave this count a name: entropy. Roughly speaking, entropy measures how many hidden arrangements of atoms would look the same from the outside. High entropy simply means overwhelmingly likely. Nothing pushes the world toward disorder. Disorder just holds almost all the tickets in the lottery. Level 44. Now the one-way flow of heat becomes something deeper. The second law of thermodynamics. It says that in any closed system, entropy tends to rise, and once it has risen, it essentially never falls back. Stir a spoonful of milk into tea and watch the pale swirl spread and vanish. No amount of careful stirring will gather the milk back into its spoonful, because the mixed arrangements outnumber the separated ones beyond all counting. What makes this law remarkable is its loneliness. Every other law we have met works the same way forward and backward in time. A planet's orbit run in reverse is still a perfectly legal orbit. The second law is the only one with an arrow built into it. It does not say what must happen. It says what is so overwhelmingly probable that, in practice, the alternative never comes. That arrow points somewhere familiar, and we follow it next. Level 45. The arrow inside the second law turns out to be pointing at time itself. Run a film of cream swirling into coffee backwards, and you know at once that something is off. And yet every molecular collision in that film obeys the laws of motion perfectly. The wrongness is entropy flowing the wrong way. The direction we call the future is simply the direction in which entropy grows, in which cream mixes, coffee cools, and shuffled decks stay shuffled. This may even be why memory points only one way. Making a record of anything in ink or in the soft wiring of a brain is a physical process, and it rides the same statistical current as everything else. You remember yesterday and not tomorrow, because your memories live on the settled side of that current. Time's arrow, roughly speaking, is not painted onto the universe. It emerges from counting one gentle improbability at a time. Level 46. If heat insists on flowing downhill, then a clever machine can charge a toll along the way. That is all an engine is. A steam engine, a car engine, a power station. Each one stands beside a flow of heat from something hot to something cold. Each skims off a share of that flow as useful work, the way a water wheel borrows from a falling stream. The second law sets a strict ceiling on the toll. Some heat must always pass through to the cold side uncollected, which is why no engine, however perfect its bearings, can turn all its fuel into motion. Sadi Carnot worked out that ceiling in the 1820s, before anyone was even sure what heat was. A refrigerator is the same machine running in reverse. It pays, with electricity, to pump heat uphill out of the cold food and into your warm kitchen. That is the gentle hum you hear at night, the sound of work being spent, so that heat, just locally, runs the way it never would on its own. Level 47. All this talk of hot and cold invites a question: how cold can cold become? Temperature, remember, is just the trembling of atoms, so there is a floor, the point where that trembling has given up all the energy it can. It's near minus 273 degrees Celsius, and physicists call it absolute zero. Deep space between the stars hovers only a few degrees above it. Laboratories on Earth have coaxed small clouds of atoms to within a billionth of a degree of the floor, colder than anywhere nature is known to have made. Yet the floor itself can never quite be touched. Each step of cooling removes less heat than the one before, and a well-tested rule says the final step would take forever. Even at the very bottom, quantum mechanics leaves a faint, irreducible tremble in place, a hum that no refrigerator can remove. That strange hum has its own levels, waiting higher up the ladder, level 48. We have leaned on atoms for many levels now without ever proving they exist. Well into the early 1900s, some serious scientists still doubted them. The proof had been hiding in plain sight since 1827. That year, a botanist named Robert Brown looked through his microscope at tiny grains shed by pollen floating in water. They jittered endlessly, as if nudged by something unseen. In 1905, Einstein explained the nudging. Each grain, he argued, is struck from all sides by water molecules far too small to see, and every so often the strikes fail to balance, so the grain lurches. He predicted exactly how far a grain should wander, on average, as the minutes pass. Jean Perrin then measured that wandering and found the prediction held grain by grain. From the visible trembling of pollen, anyone could now count the invisible molecules of water. Atoms stopped being a convenient story and became things. Level 49. Once atoms are real, some everyday magic can be seen with new eyes. Ice, water, and steam are not three substances. They are one crowd of identical molecules, holding one another in three different ways. Warm a block of ice and its temperature climbs until, at 0 degrees Celsius, it pauses. For a while, all the heat you add goes quietly into loosening the rigid lattice until the solid gives way to liquid. At 100 degrees Celsius, the liquid lets go again into steam. Physicists call these sudden collective changes phase transitions, and the important word is collective. No single molecule decides anything. Each one feels only its nearest neighbors, yet trillions of tiny local negotiations add up to one sharp, sudden agreement. The way a murmuring audience can fall silent all at once. A pond does not freeze molecule by molecule so much as it tips. Nature loves this move and uses it in places far stranger than a kettle. Level 50. We close this stretch of the ladder with a puzzle that took nearly a century to settle. James Clerk Maxwell, one of the great physicists of the 1800s, imagined a tiny doorkeeper standing at a small hole between two rooms of air. The doorkeeper watches the molecules and opens the door only at the right moments, letting fast ones gather in one room and slow ones in the other. Patiently, without pushing anything, it sorts warmth from coolness until one side grows hot while the other grows cold. Heat has run uphill, and entropy has fallen, apparently for free. For 100 years, this gentle demon haunted the second law. The resolution, when it finally came, was quiet. The demon must observe and remember each molecule, and memory is physical. Sooner or later, its little notebook fills, and erasing it, physicists showed, carries an unavoidable entropy cost that pays the whole bill. Information, it turns out, belongs to physics. Hold that thought softly. It returns near the very top of this ladder. Half of the ladder is now behind you, from a pebble at rest to the slow logic of heat. The second half begins with something smaller and stranger, a tiny spark on a piece of amber. Level 51. For 50 levels, the only pull we have needed was gravity, the gentle sag of mass toward mass. The ancient Greeks knew of another one. Rub a piece of amber with wool, and the amber gains a strange new power. It tugs at hair, at dust, at scraps of dry leaf, reaching across the air. We now call the property behind this pull electric charge, and it comes in two kinds, positive and negative. Like kinds push apart, opposite kinds draw together. And here is the quiet astonishment. Between two small particles, the electric pull is stronger than their gravity by an amount so vast it has no everyday name. Yet you rarely feel it, because the world holds almost exactly equal amounts of both kinds, mixed so finely that the pulls cancel. Gravity rules the planets only because charge hides itself. When it stops hiding, even for a moment, you get sparks and everything that comes next. Level 52. That amber tugged at dust without touching it, and this bothered careful thinkers for centuries. How does a force cross empty space? The answer that slowly took shape is one of the deepest ideas in all of physics. A charge does not reach out directly to another charge. Instead, it fills the space around itself with a condition, a readiness to push or pull, called the electric field. The field is there whether or not anything feels it, the way the smell of bread fills a kitchen before anyone walks in. Bring a second charge into the room, and it responds to the field where it stands, not to the distant charge itself. At first, the field sounded like a mere picture, a bookkeeping trick. It is not. The field carries energy. It can travel. It can even exist on its own, far from any charge at all. That last fact is quietly waiting for you a few levels up. Level 53. If charges can be pushed, they can be made to flow, and flowing charge is called a current. Picture water moving through pipes. A battery is like a quiet pump, lifting charge to a higher electrical pressure, and the wires are the pipes that carry it around. But there is one rule the water picture makes easy to see. The charge needs a complete circle to travel, a closed loop out from the pump and back again. When you press a light switch, you are not releasing something stored in the bulb. You are closing a tiny gap in a loop, letting the flow run unbroken through the thin wire inside the glass. That wire resists the flow, the way a narrow pipe resists water, and the gentle struggle heats it until it glows. Every lamp, every phone, every kettle is a loop like this. Flowing charge also does something else entirely unexpected, and that is next. Level 54. The unexpected thing is magnetism. People had known certain stones for thousands of years, lodestones, which pulled on iron and, when floated on cork, slowly swung to point north. Compass needles guided sailors long before anyone knew why they worked. Magnetism seemed a separate magic, unrelated to amber and charge. Then, in the early 1800s, a lecturer named Ørsted noticed a compass needle twitch whenever a nearby wire carried current. The needle moved as if the flowing charge had reached out and brushed it. That small twitch was the clue. Magnetism is not a separate force at all. It is what moving charge does. Wrap a wire into a coil, run a current through it, and you have built a magnet you can switch on and off. Even the lodestone obeys this rule, in essence, since inside its atoms, tiny charges are forever circulating. Electricity and magnetism were beginning to look like two faces of one thing. Level 55. If moving charge makes magnetism, a patient mind will ask the reverse question, and Michael Faraday had the most patient mind of his century. In 1831, he found the answer. A changing magnetic field pushes charge. Move a magnet through a coil of wire, and while it moves, and only while it moves, a current flows. Hold the magnet still and the current stops. That is the entire secret. Now consider what it means. Spin a magnet near coils of wire all day and all night, and charge is pushed through the wires without pause. Nearly every power plant on Earth, coal, gas, nuclear, hydroelectric, wind, is at heart just this one trick. Something spins a magnet, and a distant city lights up. The steam or the falling water merely provides the spinning. One quiet observation on a workbench in London became the steady pulse inside every wall socket you have ever touched. Level 56. By the middle of the 1800s, the clues were piled high, and James Clerk Maxwell gathered them into 4 compact equations. Charges make electric fields. There are no lone magnetic poles. Changing magnetic fields make electric fields, which was Faraday's discovery. And, in the step Maxwell added himself, changing electric fields make magnetic fields in return. Read those last 2 together slowly. A changing electric field creates a magnetic field, and that changing magnetic field creates a fresh electric field. Each one gives birth to the other, over and over, like 2 dancers each lifting the other in turn. Nothing else is needed. No charges, no wires, no magnets. The pair can leave home entirely, regenerating each other as they travel through empty space. A wave made of pure field. Maxwell worked out the speed such a wave would have to move. The number that came out of his equations made him pause. Level 57. The speed that fell out of Maxwell's equations was about 300,000 kilometers per second. And that number was already famous. It was the measured speed of light. Maxwell saw what this had to mean and wrote it down with a scientist's careful joy. Light is an electromagnetic wave. The glow of a candle, the shine on a spoon, the daylight resting on your closed eyelids, all of it is those 2 dancing fields, electric and magnetic, regenerating each other in flight. What we call color is simply how fast the fields wave back and forth. Red light waves more slowly, blue light more quickly, and your eyes translate frequency into hue the way ears translate frequency into pitch. Nothing about light was left separate anymore. The study of amber and lodestone had quietly swallowed the study of rainbows. 3 sciences, electricity, magnetism, and optics, folded gently into one. And the waving does not stop where seeing stops. Level 58. If color is frequency, there is no reason the waving must stay within what eyes can catch, and it does not. Slow the waves far down and you have radio, waves as long as buildings, drifting through walls as if they were fog. A little faster and you reach microwaves, then infrared, the soft warmth you feel from a fire across a room. Then comes the narrow band your eyes evolved to see, red through violet. Beyond violet lies ultraviolet, then X-rays, then gamma rays, with waves shorter than a single atom. All of it is the same phenomenon, the same pair of dancing fields, differing only in tempo. Here is a picture to fall asleep on. The electromagnetic spectrum is an endless piano stretching away in both directions, and human vision is a single octave somewhere near the middle. Radio songs and starlight and the warmth of a distant fire are all notes on that one keyboard, level 59. Because light is a wave, it does the things all waves do, and the loveliest of these is interference. Drop 2 pebbles into a still pond and watch the ripples cross. Where crest meets crest, the water lifts higher. Where crest meets trough, the surface goes calm, 2 motions canceling to nothing. Light does exactly this. Send it through 2 narrow slits, and the wall beyond shows stripes, bright where the waves agree, dark where they cancel. The colors drifting on a soap bubble are interference, too, reflections from the film's 2 surfaces, adding and erasing each hue in turn, and a wave that wiggles can wiggle in a chosen direction, which is called polarization. Glare from a lake is light waving mostly sideways, and polarized sunglasses are simply fences of molecules that block that orientation while letting the rest through. Tilt your head beside a bright lake someday and watch the glare quietly return. Level 60. Every wave we have met so far had a speed, so it was natural to measure the speed of light with ever greater care. Galileo tried with lanterns on distant hills and learned only that light was far too fast for him. Later astronomers timed the moons of Jupiter, and spinning mirrors in French laboratories did better still. The answer settled near 300,000 kilometers per second, fast enough to circle the Earth about 7.5 times in a single second. But hidden inside the measurements was something quietly wrong. Every other speed depends on how you move. Walk toward an approaching train, and it approaches faster. Yet light, measured from the Earth swinging one way around the sun or the other, always came out exactly the same. No chasing it made it slower. No fleeing made it faster. It is a small strangeness, easy to overlook. At the next level, this small strangeness breaks everything, gently. By the end of the 1800s, physicists had measured the speed of light from every direction, in every season, and the answer refused to change, no matter how the Earth moved through space. In a quiet patent office in Bern, a young clerk named Albert Einstein decided to take that stubborn measurement at its word. Level 61. We ended the last stretch of our journey with waves of light rippling through space at about 300,000 kilometers per second. Here is the strange part. Speeds are supposed to add. If you walk forward at 5 kilometers per hour, inside a train moving at 100, someone standing on the platform sees you gliding past at 105. That is ordinary, comfortable arithmetic, and it works for balls, birds, and trains, but light ignores it. Shine a flashlight from the front of that moving train, and the person on the platform measures the beam traveling at exactly the same speed you do, not the train speed plus light speed. just light speed, always, for everyone. Stranger still, imagine chasing a beam of light in the fastest rocket you can dream of. You would expect the beam to slow beside you, the way a car you are catching seems to crawl. It does not. It recedes from you at full speed, as if you had never moved at all. Every careful experiment agreed. Light speed is the one number the universe refuses to negotiate. Something else has to give, and what gives is waiting in the next level. Level 62. In 1905, the patent clerk made his move, and it was an act of quiet intellectual courage. Everyone else was trying to explain the measurement away, inventing invisible winds and hidden ethers to rescue common sense. Einstein did the opposite. He took the measurement as law. The speed of light is the same for every observer, he said, no matter how they move, and the laws of physics are the same for all of them too. Then he simply followed the logic wherever it led, the way you might follow a quiet road at night without knowing where it ends. The logic led somewhere astonishing. If everyone must measure the same speed for light, then something we always thought was solid has to bend instead. That something is time. Two people moving past each other cannot share one universal clock. Each carries their own time along with them, personal and slightly different, like passengers on a night train, each wearing their own quiet wristwatch. Distance bends as well, as we will soon see. The old stage of absolute space and absolute time was gently dismantled by a clerk working in his spare hours. Level 63. Follow that logic one step further, and you arrive at time dilation, the gentle rule that moving clocks run slow. A clock carried past you at great speed genuinely ticks more slowly than the clock on your nightstand, not because its gears are faulty, but because time itself flows differently along its path. At everyday speeds, the effect is fantastically small, far too small to notice on any commute, but nature runs the experiment for us constantly. High above your roof, cosmic rays strike the upper air and create tiny particles called muons. A muon lives, on average, for about 2/millionths of a second before it fades away. Even moving at nearly the speed of light, that brief life should end long before the ground arrives. Yet muons reach the surface in great numbers, drifting harmlessly through the air around you right now. From our point of view, their inner clocks are slowed by their tremendous speed, so their short lives stretch just enough to complete the journey down. Time dilation is not philosophy or metaphor. It is falling gently out of the sky above your bed every moment of every night. Level 64. If time can stretch, then distance must answer for it too, and so must the very idea of now. A fast-moving object is measured to be shorter along its direction of travel, a quiet effect called length contraction. The muon, from its own point of view, keeps its ordinary brief life, but sees the atmosphere compressed into a thinner layer it can cross in time. Both descriptions are true, and both agree on what actually happens. Stranger still is what happens to simultaneity. Einstein imagined a long train passing an embankment when lightning touches both ends, front and back, at what a person standing beside the track calls the very same instant. But a passenger seated at the center of the moving train is gliding toward one flash and away from the other. so the light from the front reaches her first. For her, honestly and correctly, the front strike happened before the rear one. Neither observer is mistaken. There is simply no universal now stretching across the universe, no single cosmic moment shared by all. Your now, in essence, belongs to you alone, and the universe keeps perfect books anyway. Level 65. Later in that same year of 1905, Einstein noticed a consequence hiding quietly inside his own equations, and it became the most famous line in all of physics. E equals mc squared. Energy equals mass times the speed of light multiplied by itself. What it says in essence is that mass is frozen energy, energy at rest, sitting patiently in the form of matter. And because the speed of light is such an enormous number, and it gets multiplied by itself, even a tiny amount of mass holds an almost unreasonable amount of energy. Take a single paper clip, a gram or so of ordinary metal resting in a desk drawer. If all of its mass could somehow be converted into pure energy, it would release, roughly speaking, enough to power a whole city for a day. The warmth of the sun on your face works exactly this way. Deep in its core, hydrogen fuses into helium, and a small sliver of mass goes missing in every reaction, released as the light that crosses space to find you. Every sunbeam is a little of the sun's own substance, spent gently on your behalf. Level 66. A few years after those papers, Einstein's former mathematics teacher, Hermann Minkowski, saw the deeper picture hiding beneath them. Space and time, he realized, are not separate things at all. They are woven together into a single four-dimensional fabric, which we now call space-time. The events of your life are not merely places. They are places joined to moments, points stitched into one weave. And here is a lovely way to hold the idea as you drift in essence. Everything in the universe moves through space-time at one fixed rate, always. Lying still in your bed, you are not motionless. All of your motion is pouring through time, carrying you steadily from this moment into the next. When something rushes through space, it borrows from that flow, so its passage through time slows down, which is exactly the time dilation we met a few levels ago. Speed through space plus speed through time, roughly speaking, always adds up to the same total. Light spends everything on space and nothing on time. You, resting quietly tonight, are spending nearly everything on time. Both of you are traveling, and this fabric can do more than hold still. It can bend. Level 67. In 1907, still at his desk in the patent office, Einstein had the idea he would later call the happiest thought of his life. A person falling freely, he realized, does not feel their own weight. Fall gently in your imagination, and every loose object falls with you, floating calmly at your side, as if gravity had been switched off. You have seen this truth in footage of astronauts drifting inside their station. They are not beyond Earth's gravity at all. They are simply falling around the planet endlessly together with their ship. Now turn the thought over. Stand inside a closed elevator far from any planet, accelerating smoothly upward, and your feet press into the floor exactly as they do at home. Drop an apple in that elevator, and it lands just as it would in your kitchen. No experiment performed inside can tell the difference between gravity and steady acceleration. They are, in essence, the same experience. That simple observation that a falling person feels nothing became the seed of an entirely new theory of gravity. It took 8 patient years to grow, and it is waiting in the next level. Level 68, in 1915, the seed flowered into general relativity, Einstein's theory of gravity, and it changed what gravity even means. Gravity, it turns out, is not a force reaching across empty space the way Newton had pictured it. It is the shape of spacetime itself. Matter and energy bend the fabric around them, and things moving through the bent fabric follow the straightest paths available, which look to us like curves. Physicists like to say it in one slow breath, and it is worth hearing slowly. Matter tells space-time how to curve. Curved space-time tells matter how to move. Picture a heavy sleeper resting in the middle of a soft mattress, and a marble placed near the edge, rolling gently inward. The marble is not pulled by any rope or beam. It simply follows the shape of the surface it lives on. The Earth does the same in the curved spacetime around the Sun, coasting along the natural contours of the fabric. And the apple that fell near Newton all those levels ago is finally explained in full. It was never tugged downward. It was following the honest shape of a universe curved by the quiet mass of the Earth. Level 69. If mass curves space-time, a natural question follows softly. What happens when the curvature runs away with itself? Squeeze enough mass into a small enough space, and the bending becomes so steep that nothing, not even light, can climb back out. The result is a black hole, first glimpsed in the mathematics by Carl Schwarzschild only months after Einstein published his theory. Around every black hole lies a boundary called the event horizon. It is not a wall and not a surface you could ever touch. It is simply a one-way door drawn in empty space. Whatever drifts across it does not return. Time behaves strangely near that edge. Watched from far away, a clock falling toward the horizon seems to tick more and more slowly, its light growing dimmer and redder until the clock appears to freeze at the boundary, fading rather than crossing. From the clock's own point of view, nothing special marks the moment. It simply continues falling. Both stories are true, each in its own frame. For decades, these objects seemed like mathematical ghosts, too strange to be real. The universe, it turned out, builds them routinely, and we will meet their echo shortly. Level 70. All of this might sound like distant theory, yet you have probably held the proof in your hand today. The satellites that guide a phone's maps carry atomic clocks, and those clocks feel both sides of relativity at once. They race along their orbits, so special relativity slows them slightly. They also sit higher above the Earth, where spacetime is less curved, so general relativity runs them slightly fast. Engineers must correct for both effects together, a few dozen millionths of a second every single day. Left uncorrected, the errors would quietly pile up, and your position on the map would drift by kilometers within a day. Einstein rides in your pocket every time you find your way home. And in 2015 came something grander still. 2 black holes, spiraling together far across the universe, sent ripples through the fabric of space-time itself. The gravitational waves Einstein had predicted a century earlier. Detectors on Earth felt space stretch and relax by less than the width of a single proton and heard it as a soft, rising chirp. Spacetime is real, and it rings. Yet at the very smallest scales, the world keeps one more surprise, waiting just a few levels up. Relativity had repaired the physics of the very fast and the very heavy, and for a moment the house of science seemed whole again. But down among the atoms, in the world of the very small, physics was quietly preparing to break a second time. Level 71. The story of the very small begins, of all places, with an oven. By the end of the 1800s, physicists understood heat, and they understood light, and they tried to join the two with a simple question: how much light should a warm, enclosed box give off at each color? The classical answer came from counting the ways waves can fit inside the box. Long, lazy waves fit in only a few ways. Shorter waves fit in more and more ways without end, and so the theory handed every warm object an unlimited budget of harsh ultraviolet light. Taken seriously, the prediction said that a kitchen oven set for bread should flood the room with rays beyond violet endlessly. This failure earned a dramatic name, the ultraviolet catastrophe. And yet the real world stayed calm. Coals glow a soft orange, ovens bake quietly, and the glow of any warm body always fades away at the short wavelengths instead of growing. The gap between that prediction and the evening calm of a kitchen was not a small error to be patched. Something at the very root of physics was wrong. Level 72. The rescue came in 1900 from a careful and rather conservative German physicist named Max Planck. He found he could match the true glow of warm objects perfectly, but only by making one strange assumption. Energy, he supposed, could not flow out of matter in a smooth stream. It had to leave in tiny separate packets, which he called quanta, each packet sized in proportion to the frequency of the light. It was as if nature refused to pour water and would only hand out ice cubes. The packet size is set by a number now called Planck's constant, and it is almost unimaginably small, which is why everyday life still feels smooth and continuous. Planck himself did not like his own idea. He called it an act of desperation and spent years hoping someone would explain it away. No one ever did. Because high-frequency packets are expensive, a warm oven simply cannot afford to emit much ultraviolet light, and the catastrophe dissolves. The night stays safely dark, and so does your kitchen. But the packets were more real than Planck dared to believe. As a young patent clerk was about to show, 73, that patent clerk was Albert Einstein, and in 1905 he took Planck's packets more seriously than Planck ever had. He studied a puzzle called the photoelectric effect, in which light falling on a metal surface knocks electrons loose. If light were a smooth wave, then a bright enough lamp of any color should eventually shake electrons free. That is not what happens. Dim blue light frees electrons at once, while brilliant red light on many metals frees none at all. Einstein's explanation was simple and startlingly bold. Light itself arrives in packets, each carrying an energy fixed by its color, and an electron escapes only if one single packet hands over enough. Red packets are individually too poor, no matter how many of them arrive. It is like a gate that opens for one sufficient coin. 1,000 small coins offered one at a time will never open it. These packets of light were later named photons, and this work, not relativity, earned Einstein his Nobel Prize. After 2 centuries of confident wave theory, light was behaving as particles again. Somehow, both pictures would have to be true at once. Hold that thought gently. Level 74. If light comes in packets, atoms begin to make a new kind of sense. In 1913, the Danish physicist Niels Bohr pictured the hydrogen atom as something like a ladder. The electron circling the nucleus is not allowed to sit at just any distance with just any energy. It may rest only on certain rungs, certain permitted levels, and nowhere in between. When an electron drops from a higher rung to a lower one, the atom releases the difference as a single packet of light with one exact color. To climb, it must absorb exactly that much. This one idea explained something chemists had known for decades, that every element, when heated or electrified, shines in its own precise set of colors, a fingerprint of bright lines. Neon glows that particular red-orange because those are the gaps between the rungs of neon's ladder, and no other colors are on offer. Bohr's model was rough, half classical and half new, and he knew it. But it worked far too well to be an accident. The rungs were real. Why nature builds ladders at all was a question waiting just a level or two up. Level 75. The answer began with a French graduate student named Louis de Broglie in 1924. His reasoning had a beautiful symmetry. If light, which everyone had called a wave, can behave as particles, then perhaps electrons, which everyone called particles, can behave as waves. He proposed that every moving piece of matter carries a wavelength, shorter for heavier and faster things. For a thrown baseball, the wavelength is absurdly tiny, far too small ever to notice, which is why baseballs never look wavy. For an electron, it is comparable to the spacing of atoms in a crystal, and that suggested a test. Within a few years, experimenters fired electrons at crystals and watched them scatter into ringed patterns of preferred directions, exactly the way water waves ripple past the pilings of a pier, reinforcing in some places and canceling in others. Particles do not do that. Waves do. Electrons, unmistakably, did. And de Broglie's waves even whispered an answer to Bohr's ladder. The allowed orbits are the ones where a whole number of electron wavelengths wraps neatly around the atom, like a standing wave humming on a circular string. The rungs are where the wave fits, level 76. If electrons are waves, something must describe how those waves move, and in 1926, Erwin Schrödinger wrote down the equation that does. It governs a quantity physicists call the wave function, written with the Greek letter psi. Psi is not a ripple in water or in air. It is best described, roughly speaking, as a wave of possibility. Where the wave runs high, the electron is likely to be found. Where it runs low, unlikely. Until anyone looks, the wave simply flows smoothly and predictably, spreading through space the way the scent of coffee drifts through a quiet morning kitchen. Schrödinger's equation gives the shape of that flow at every future moment with complete certainty. Chance enters only at the end, when a measurement is made and the electron turns up at one definite place, as if the whole spread out wave had answered a question with a single word. This double life, smooth flowing possibility, followed by one abrupt fact, sits at the very heart of the quantum world, and it is waiting for us again at level 80. For now, rest with the gentler half. The wave itself is calm, level 77. Waves come with a built-in trade-off, and in 1927, Werner Heisenberg saw what it meant for matter. Think of a single note of music. A long, sustained note has a pitch you can name, but a sound lasting only an instant, a brief click, has no definite pitch at all. To be short in time, a wave must be a blend of many frequencies. The wave of an electron obeys the same arithmetic. Squeeze it into a narrow region, so its position is sharp, and it necessarily becomes a blend of many wavelengths, which for matter means many momenta. Let its momentum be sharp instead, and the wave must spread wide, so the position blurs. Heisenberg's uncertainty principle says the two sharpnesses multiplied together can never shrink below a fixed limit set by Planck's tiny constant. Notice carefully what this is not. It is not clumsiness, not the disturbance of a rough measuring touch, and not a gap in our knowledge waiting to be filled. A quantum object simply does not possess an exact position and an exact momentum at the same time, any more than a click possesses a pitch. Reality itself is softly focused, level 78. Because the wave function is a wave, it can do what all waves do, which is pass through two openings at once and interfere with itself. Here is the experiment that carries the whole mystery. Send electrons toward a barrier with two narrow slits, one electron at a time, with long pauses in between, and record where each lands on a screen beyond. Each arrival is a single tiny dot, a particle's signature. But as the dots accumulate over hours, like raindrops slowly speckling a dry pavement, they build up stripes, bands where electrons land often, and bands where they almost never land at all. Stripes are interference, the signature of a wave that went through both slits together. Each electron, in some honest sense, explored both paths, and its possibilities overlapped and canceled. Now place a detector at the slits and ask which path was taken. The question gets an answer, one slit or the other, and the stripes quietly vanish. Unmeasured, the electron is a superposition, both routes at once. Measured, it is one thing in one place. Nature seems to hold every option open until an observation asks it to choose. Nobody fully knows why. Level 79. Two more quiet marvels follow from the wave picture. The first is tunneling. Because a wave function fades gradually rather than stopping dead, a particle pressed against a barrier, it lacks the energy to climb, still keeps a small tail of possibility on the far side, and sometimes it is simply found there, like a marble left in a bowl turning up, on rare occasions, just outside it. This is not idle speculation. Deep in the sun, protons repel each other so strongly that by classical arithmetic they should almost never meet and fuse. They fuse anyway, by tunneling through the barrier, and that is part of why sunlight falls warm on your face. The second marvel is entanglement. Two particles born from one event can share a single wave function, so that measuring one instantly settles what the other will show across any distance at all. Einstein distrusted this, famously calling it spooky action at a distance, and hoped the particles simply carried hidden instructions from birth, like matched gloves packed in separate boxes. Careful experiments later ruled that comfort out. The correlations are stronger than any prearranged plan allows, yet no usable message can be sent this way. The universe stays gently discreet. Level 80, all of this leaves one question standing, and it is the deepest in the subject. The wave function flows smoothly, says Schrödinger, until a measurement happens, and then a single outcome appears. But what exactly counts as a measurement, and what happens in that moment? The Copenhagen interpretation, gathered around Bohr, says the wave function is a tool for predicting outcomes, that it collapses when an observation is made, and that asking what happens behind the curtain is not a physical question. The many worlds view, proposed by Hugh Everett in the 1950s, says the wave never collapses at all. Every outcome happens, and the world, observer included, branches, each version seeing one result. Both views predict the same experiments, so experiment cannot yet choose between them. And here is the strangest part to fall asleep on. Quantum mechanics is the most precisely confirmed theory human beings have ever produced, verified to many decimal places, quietly running every transistor in the phone beside your bed. We can use it flawlessly and still disagree about what it says the world is. The math is settled, the meaning is not. Ahead, these waves become something grander still. They become fields, filling all of space. Quantum mechanics had passed every test the world could devise, and its strange rules were now simply how nature worked. So physics took this new instrument and aimed it at the deepest place it knew, the heart of matter itself, level 81. The journey inward did not stop at the atom. At the center of every atom sits the nucleus, a dense little knot of particles called protons and neutrons, crowded into a space roughly 100,000 times smaller than the atom around it. If the atom were a great cathedral, the nucleus would be a grain of sand resting quietly at the center of the floor. For a while, physicists hoped this was the bottom of the world: protons, neutrons, and electrons. 3 ingredients, 1 recipe, everything that exists. Then they built accelerators, vast rings and tunnels that push particles nearly to the speed of light, and let them collide so the debris could reveal what matter is made of. Out of those collisions came new particles nobody had asked for. Then more again. By the middle of the 20th century, there were hundreds of them, with odd names and lives shorter than a blink, flickering into existence and fading away. Physicists called it the particle zoo, half in wonder and half in weariness. Nobody believed nature could truly be that cluttered. The idea that would restore order is waiting at the next level. Level 82. Order arrived in 1964 when Murray Gell-Mann, and independently a young physicist named George Zweig, proposed that the zoo was a catalog of combinations, not a catalog of ingredients. Beneath nearly all those hundreds of particles lay a small family of truly fundamental pieces. Gell-Mann called them quarks, borrowing the odd little word from a playful line in a novel by James Joyce. The proton, it turned out, is not fundamental at all. It is a triplet, 3 quarks bound together, 2 of one kind and 1 of another. The neutron is a triplet as well, with the mixture reversed, and all the strange, short-lived creatures of the zoo were simply other arrangements, other groupings, the way a handful of letters can spell hundreds of different words without a single new letter being invented. Think of how it feels when a cluttered drawer finally makes sense, when you see that the tangle is really just a few kinds of things repeated. That is what the quark idea did for physics. The zoo became an alphabet. Matter, at the bottom, is spare and tidy. What holds those quarks together, and why no one has ever caught a quark alone, is waiting a few levels up, level 83. With quarks in place, the ingredients of the world were nearly settled, and attention turned to what the ingredients actually do. Here, physics offers one of its calmest and most sweeping statements. Everything that ever happens, anywhere, is the work of just four forces. Gravity, which gathers planets and holds you gently against your bed tonight. Electromagnetism, which is light and electricity and magnetism, and also every touch you have ever felt, since the atoms of your hand never truly meet the atoms of a door. They only push electrically at close range. The strong force, which grips quarks into protons and binds the nucleus against the electric repulsion trying to loosen it. And the weak force, quiet and rare, which lets one kind of particle transform into another. That is the entire list. A falling leaf, a candle flame, a heartbeat, a distant star, the warmth of a cup in your hands. Four forces in different mixtures and nothing else. It is a short menu for such a rich world. In the levels ahead, we will visit each of these forces in turn, and we will find that they are stranger and more beautiful than the list makes them sound. Level 84. Before visiting the forces, physics had to say more carefully what a particle even is, and the answer changed everything. In the mature theory, the deepest ingredients of the world are not little balls at all. They are fields, invisible, continuous somethings that fill all of space, the way the surface of a still pond fills the whole pond. A particle is a ripple in its field. There is one electron field spread through the entire universe, through this room, through your body, through the space between galaxies. Every electron that exists is a small traveling ripple in that single field, one note played on one instrument. This is why every electron in the universe is exactly, perfectly identical. Why the electrons in your eyelashes match the electrons in the farthest star. They are not similar objects made in similar factories. They are the same field, rippling. There is a field for the photon, a field for each kind of quark, a field for every fundamental particle on the list. Empty space, in this picture, is not empty. It is all the fields at rest, a pond with no ripples, quietly waiting. Hold that image of the still pond. The next level sets it talking. Level 85. If particles are ripples in fields, then forces need a new description too, and it turns out to be a sociable one. In this picture, two particles exert a force on each other by exchanging messenger particles. Little ripples passed back and forth between them. When two electrons repel, they are trading photons, the particles of light, and the exchange itself is what pushes them apart. The picture is imperfect, but you can imagine two people on smooth ice tossing a heavy ball back and forth. each toss nudging them a little away from each other. Each force has its own messengers. Electromagnetism speaks in photons. The strong force speaks in particles called gluons, named, quite honestly, for the way they glue quarks together. The weak force speaks in two heavy messengers, known as W and Z. Roughly speaking, a force is a conversation, a constant quiet exchange, and what we feel as pushing and pulling is the accumulated weight of countless tiny messages. Even the magnet holding a drawing on your refrigerator is not gripping in silence. It is murmuring endlessly in photons. Whether this strange picture truly matches reality was a fair question. The next level gives the answer, and it is one of the proudest in all of science, level 86. The first force to receive its full quantum treatment was electromagnetism, and the resulting theory is called quantum electrodynamics. It describes how light and electrons dance together, and it was completed around the middle of the 20th century by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, each finding his own path to the same answer. What makes this theory remarkable is not its elegance, though it is elegant. It is the agreement with experiment. The theory predicts, for example, the precise strength of the electron's tiny magnetism, and when that prediction is set beside the measured value, the two match to roughly 1 part in a billion. Feynman liked to say this was like measuring the distance from New York to Los Angeles to within the width of a single human hair. No description of nature in any field of human effort has ever been tested so finely and held so well. Whatever unease anyone still felt about ripples and messenger particles, the numbers were serene. Quantum electrodynamics is, in essence, the most precisely confirmed theory our species has ever produced, and it became the template. Physicists would spend the following decades building theories of the other forces in its image, as we are about to see. Level 87. The strong force received its own theory in the same style, with gluons as messengers, and it holds one of nature's strangest rules. Quarks can never be alone. Most forces fade with distance, the way a magnet's pull weakens as you draw it away. The strong force does the opposite. Try to pull two quarks apart, and the bond between them behaves like an elastic band, storing more and more energy the farther you stretch it. And here the deepest bookkeeping of physics steps in, the old truth that energy and mass are two forms of one thing, E equals mc squared. Stretch the band far enough, and the stored energy grows so large that nature spends it on making new quarks. The band parts, and each loose end is instantly capped with a freshly created quark. You reached for one free quark, and you are left holding two complete pairs. It is as if every piece of string you cut quietly grew new ends. Because of this, no experiment has ever caught a single quark on its own, and the theory says none ever will. Quarks live in permanent company, sealed gently inside protons and neutrons, all the way down. Level 88. The weak force is the quietest of the four, and the only one that changes what things are. Gravity pulls. Electromagnetism pushes and pulls, the strong force binds. Only the weak force transforms, turning one kind of particle into another. This is the engine of radioactive decay, a lone neutron, left entirely to itself, will after some minutes quietly become a proton, sending away an electron and a ghostly little particle, the antineutrino, a shy cousin of light. Nothing struck it. The weak force simply allows matter to change its identity, and so, now and then, it does. And this shy force keeps you alive. The sun shines by fusing protons together, and the very first step requires a proton to transform into a neutron, which only the weak force can arrange. Because the weak force is so feeble, that step almost never happens, and the sun burns its fuel with astonishing patience, like a fire whose kindling barely catches. If the weak force were strong, our star would have used up its fuel long ago. Because it is weak, the sun has burned steadily for billions of years, long enough for oceans, for forests, for evenings, for you, drifting towards sleep. One more field remains to meet, and it is the strangest of all, level 89. One puzzle remained in this family of fields, the simple question of why particles weigh anything at all. The equations, in their barest form, preferred every particle to be massless, moving forever at the speed of light. The answer, proposed in 1964 by Peter Higgs and, independently, by Robert Brout and Francois Englert, is one more field, a field that fills the entire universe with a kind of quiet thickness. Particles moving through the Higgs field are, roughly speaking, resisted by it, and that resistance is what we experience as mass. Picture a famous face crossing a crowded room. The crowd gathers close, and the visitor finds it hard to speed up and hard to stop. An unknown guest slips through untouched. The photon ignores the Higgs field completely, and so it stays massless, gliding at the speed of light forever. The electron feels the field faintly, and heavier particles feel it strongly. For almost 50 years, this field remained a beautiful guess. Then, at CERN, in a machine called the Large Hadron Collider, physicists shook the field hard enough to make it ripple, and a ripple in a field is a particle. In 2012, they announced it plainly. The Higgs field is real. Level 90, behind all these fields and forces, runs a single quiet idea, and it was uncovered by a mathematician named Emmy Noether around 1915. Her theorem says, in essence, that every symmetry of nature hides a conservation law. A symmetry, here, means a change that changes nothing. If the laws of physics work the same today as they did yesterday, that sameness in time forces energy to be conserved. If the laws are the same here as they are across the street, that sameness in space forces momentum to be conserved. If they are the same facing north as facing east, then spinning things must keep their spin. You may remember, far back at levels 31 and 32, the strict ledgers of physics, the accounts of energy and momentum that always balance no matter what happens. Noether showed why those books balance. They were never separate rules. They were symmetries all along, the universe's calm indifference to when and where, written out as arithmetic. It is one of the deepest results in all of science, found by a woman her era barely allowed to lecture, and it points forward. In the final levels, symmetry stops being quiet bookkeeping and becomes the master key to everything. You are near the top of the ladder now, higher than most people ever bother to climb. From here on, the ideas are the ones physicists themselves are still climbing. The questions that stay open at the edge of what anyone knows. Level 91. In the last levels, you watched symmetry become a source of law, with conserved quantities falling out of every pattern that stays the same. Now that idea deepens into the strangest and most powerful demand in all of physics. Imagine a rule that must hold not just everywhere at once, but separately at every single point in space. Picture a hallway of clocks, each on its own wall, and a decree that you may reset any one of them by any amount without changing anything that matters. For ordinary physics, that would be chaos. The only way the world can obey such a local freedom is if something travels between the points, constantly comparing them, constantly compensating. That something is a force field. This is called gauge symmetry, and it turns the logic of physics inside out. We used to think forces simply existed and symmetries were their pleasant side effects. In the 20th century, physicists realized it is closer to the reverse. Demand that the quantum phase of the electron can be shifted independently at every point, and electromagnetism is forced into existence, photon and all. Demand richer local symmetries, and the nuclear forces appear with their exact strange characters. The forces are not decorations on the world. They are what the world must contain in order to keep its deepest promises. Two of those forces, it turns out, are secretly one, and that reunion is waiting at the next level, level 92. You have just seen that forces are the price of local symmetry, each one summoned by a pattern the universe insists on keeping. Now watch two of those forces melt together. Electromagnetism is long-ranged and familiar, the force of light and static and magnets on refrigerators. The weak force is short-ranged and shy, the force that lets the sun burn and certain atoms slowly change. On the surface, they could hardly be more different. But in the 1960s, physicists including Sheldon Glashow, Abdus Salam, and Steven Weinberg worked out that at very high energies, the two are a single force, described by one shared symmetry. Think of water and ice. In a warm room, they look like two different substances, one flowing, one rigid. Cool the room and warm it again, and you see they were always one thing, wearing two costumes. The early universe was hot enough that electromagnetism and the weak force flowed together as one electroweak force. As the cosmos cooled, the symmetry between them froze and hid, the way liquid water hides inside every ice cube. The Higgs field is what did the freezing, giving mass to some of the force carriers and leaving the photon light and free. Two rungs of the ladder turned out to be one rung seen twice. The map that gathers everything found so far is waiting one level up, level 93. That merger of forces sits at the heart of the grandest inventory science has ever written, and it deserves a level of its own. It is called the Standard Model of Particle Physics. Think of it as a periodic table for everything, but far shorter and stranger. 6 kinds of quark, which build protons and neutrons. 6 kinds of lepton, including the electron and the ghostly neutrinos. A handful of force carriers, the photon among them, each demanded by a gauge symmetry, and one quiet field lying across the whole arrangement, the Higgs, giving mass to the rest. Everything you have ever touched, tasted, or tripped over is some arrangement of a few entries on that one short list. The Standard Model is among the most precisely tested theories human beings have ever produced. Some of its predictions match experiment to about 1 part in a billion, agreement finer than any other description of nature ever written down. And yet everyone who works with it agrees it cannot be the end. It says nothing about gravity. It offers no candidate for the unseen matter that outweighs everything visible. It does not explain why the universe holds matter rather than nothing at all. A stunningly complete map with the edges plainly torn. One of those torn edges turns slowly in the sky every night, and it is next. Level 94, the Standard Model, complete as it seems, is silent about most of the matter in the universe. And here is how we know that matter is there. Watch a galaxy spin. A galaxy is a slow carousel of stars, turning once over hundreds of millions of years. The stars at the outer edge should move lazily, just as the outer planets of our solar system drift more slowly than the inner ones, because gravity thins out with distance. But when astronomers, most famously Vera Rubin, measured the outskirts of galaxies, the outer stars were moving far too fast. At those speeds, given the visible mass, they should gently drift away, like riders easing off a carousel that turns faster than its handles allow. They do not drift away, so something unseen must be holding them. A vast halo of extra mass that gives off no light at all. Weighing the universe by its gravity tells us there is roughly 5 times more of this dark matter than of everything we can see. Every star, every planet, every page of every book is the minority ingredient. Nobody knows what dark matter is. It may be an undiscovered particle drifting through you gently even now, touching nothing. Decades of patient experiments deep underground have listened for it and heard only silence so far, and matter is not even the strangest missing piece. The emptiness between the galaxies holds a surprise of its own. One level up, level 95. If dark matter is unseen weight holding galaxies together, the next mystery is stranger still. A gentle push hiding in empty space itself. Ever since the discovery that the universe expands, everyone expected the expansion to be slowing down. Gravity pulls, and pulling should act like a brake. Toss a ball upward, and it rises ever more slowly. That is what the cosmos ought to do. But in the late 1990s, 2 teams of astronomers used distant supernovae as standard beacons to clock the expansion through history, and they found the opposite. The expansion is speeding up. It is as if you tossed the ball upward and watched it climb faster and faster into the sky. Something is pushing outward, and the simplest reading of the equation says, the push belongs to space itself. Empty space, with everything removed, seems to carry a small built-in energy, and that energy stretches the universe faster the more space there is. Physicists call it dark energy, which is an honest name because it mostly means we do not know. Roughly speaking, it makes up about 70% of everything, with dark matter most of the rest, and ordinary matter a few percent, a thin bright film on a dark ocean. Whatever it is, it now steers the fate of the cosmos. And to understand a universe that is stretching, it helps to run the film backward, which is exactly what the next level does. Level 96. An expanding universe hands you an invitation that is almost impossible to refuse. If everything is drifting apart today, then yesterday everything was closer together. Run the film backward, reverse the expansion, and the galaxies glide toward one another. Keep reversing, and the universe grows denser, and anything compressed grows hotter, like the air in a bicycle pump warming under your thumb. Far enough back there are no galaxies, no stars, no atoms, only a hot, smooth, brilliant fog of particles filling all of space. This is the Big Bang picture, and it is not a guess. It is what the equations of gravity, run in reverse, insist upon, and it has passed every test we have found a way to give it. The most beautiful test comes from the first few minutes. When the whole universe was briefly as hot as the core of a star, it did what the cores of stars do. It fused the lightest nuclei, cooking hydrogen into helium before the expansion cooled everything, and the cooking stopped. The theory predicts how much of each should have been made, roughly 3/4 hydrogen and 1/4 helium by mass, with faint traces of a few other light elements beside them. We look out at the oldest gas we can find, and that is what we see. The early universe even left us a photograph of itself. It is still arriving, and it is waiting at the next level, level 97. If the young universe was a glowing fog, then somewhere there should still be light left over from it. And there is. It falls on the earth from every direction, every moment of every day. For its first several 100,000 years, the universe was so hot that atoms could not hold together, and light scattered endlessly through the haze, like headlights in thick mist. Then, at an age of about 380,000 years, the cosmos cooled enough for electrons to settle into atoms. The fog cleared everywhere at once, and the light that was flying at that moment has been traveling ever since. Stretched by the expansion into faint microwaves, it is called the cosmic microwave background, a baby picture of the entire universe still arriving. It was found in 1965, almost by accident, by Arno Penzias and Robert Wilson, two scientists puzzled by a soft hiss. Their antenna refused to give up. They cleaned the instrument, they evicted the pigeons roosting inside it, and the hiss remained because the hiss was the afterglow of the beginning. Today we have mapped that ancient light in exquisite detail. Its faintly warmer and cooler patches are the seeds that grew into galaxies, our own among them. The oldest thing you can ever observe is arriving right now, gently, everywhere. What it cannot show us is the very first instant, and the reason why sits at the next level, level 98. Behind the afterglow lies the very beginning, and there our two greatest theories stop cooperating. This level is about the most famous unfinished chapter in physics. General relativity describes gravity as the smooth bending of spacetime, a calm and continuous geometry, and within its realm it has never failed. Quantum mechanics describes matter as jumpy and uncertain, ruled by chance and interference, and within its realm it has never failed either. The trouble is that they describe the same universe. Imagine two maps of the same city, each flawless on its own side of the river, that simply refuse to agree about the bridge. Most of the time, the disagreement stays hidden Because gravity matters for big, heavy things, and quantum effects matter for tiny, light things, and the two rarely meet. But they do meet. They meet in the heart of a black hole, where a great mass is drawn down to quantum sizes, and where physicists still argue over whether the information carried by everything that falls in, the same quiet currency you met at level 50, can ever truly be lost. They meet at the first instant of the Big Bang, when the whole universe was smaller than an atom. At those meetings, our equations break down and return nonsense, which is mathematics gently telling us that something is missing. What is needed is a quantum theory of gravity, a description in which spacetime itself can flicker and blur. Nobody has completed one, though not for lack of trying. The boldest attempts so far are dreams worth hearing about, and they are next. Level 99. Physicists have not been idle in front of that unfinished chapter, and this level is about the two most famous attempts to write it. Both are beautiful. Neither is confirmed. That honesty matters. The first is string theory. It proposes that the particles we have been calling points are really tiny vibrating strands, far smaller than anything we can probe. Just as one violin string can sound many different notes, one kind of string could vibrate in many different ways, and each way of vibrating would appear to us as a different particle. An electron would be one note, a quark another, and, remarkably, one of the notes comes out looking like the carrier of gravity. The mathematics prefers extra dimensions of space, curled up too small to see, which is either a revelation or a warning, depending on whom you ask. The second is loop quantum gravity. It leaves the particles alone and instead reimagines space itself, weaving it from tiny discrete loops so that area and volume come in smallest possible pieces, like a fabric that looks smooth from across the room and is threads up close. Both ideas are ambitious, elegant, and, so far, untested by experiment. They are candidate dreams, and physics has learned to hold its dreams to a hard standard. Perhaps one of them is right, perhaps neither. Someone alive today may find out. Meanwhile, there is one level left, and it belongs to you, level 100. So here you are, at the top of the ladder, and the only thing left to do is turn around slowly and look back down. Far below, in the earliest levels, a pebble rests on the ground, and you learn that things keep doing what they are doing unless something intervenes. An apple fell, and the same pull that dropped it turned out to hold the moon in its orbit. Energy appeared as a strict ledger that nothing ever escapes, and heat turned out to be motion too small to see. Time revealed its arrow, pointing wherever disorder grows. Light was unmasked as a flying wave of electric and magnetic fields, and then the fields themselves became the deepest things there are. Space and time softened and bent, and gravity became geometry. The atom opened into a quantum world of chance and interference, where particles argue over every path at once. And finally, symmetry, quietly present from the first level, stepped forward as the author of the forces themselves. It was never 100 separate ideas. It was one story about motion told more and more carefully, from a pebble that does not move to fields that cannot help but exist. The people who told it were ordinary and curious, and they were wrong constantly, and they kept going. The story is not finished. You have seen exactly where it frays. And still, what a thing to know, lying here in the dark. The universe lets itself be understood, at least a little. That may be the quietest miracle of all. And that is the whole ladder, all 100 levels, from a pebble at rest to the edge of what anyone knows. If you are still awake, you have permission to stop climbing now. Fully. The work is done, and none of this will be on a test. Whatever level you reached tonight before the words became a river, that was the right level. The ladder does not mind. It has stood for centuries, and it will be standing tomorrow night, exactly where you left it. That is the quiet game of this channel, if you want it. Some nights you may drift away at the falling apple. Some nights you may make it to the bending of starlight, or the arguing atoms, or all the way up here to the questions with no answers yet. Every stopping point is a good one, because every level was once the outermost edge of human understanding, and someone once fell asleep wondering about it. Just as you are now, there was never a finish line hidden anywhere in this. The point was not to reach the top. The point was the slow climbing itself, one gentle idea at a time, until the ideas carried you somewhere soft. The pebble is still resting where we left it, at the very bottom of the ladder. It has not moved all night. Nothing needed it to. The stars above your roof are burning by rules you have now heard described. The light in your room, when you switched it off, obeyed equations you now know by name. The universe will keep expanding while you sleep, gently, asking nothing of you. Let the ideas settle where they like. Let the ladder fade. You climbed well tonight. Rest now. Good night.